Alright, you are welcome again. Today, let's consider vector differential operator. Okay, now, in what we are going to treat today, look at this. We say if a and b are scalar functions, then the gradient of ab is equal to a gradient of b plus b gradient of a. Okay, so we call this the gradient of product of scalars. Gradient of product of scalars. That is, product of scalars, you take the gradient of it. Okay, good. Now, please pay attention. Let's take it gradually. First of all, what is gradient? Going with the definition, gradient being a vector differential operator. Look at the symbol, nabla, or we call it del. Okay, so we say that it is the partial derivative with respect to x on I component plus the partial derivative with respect to y on j component and the partial derivative with respect to z on k component. Okay, the partial derivative with respect to x, y, z on I, j, k components. All right, good. For instance, let's assume that we have a function, a scalar function phi. Now, when we say grad phi or the gradient of phi, we are talking about the partial derivative of this phi with respect to x, y, z on I, j, k component. All right, good. Now let's go. We have the gradient of AB is equal to A, the gradient of B, plus B, the gradient of A. We have to prove that the left-hand side is equal to the right-hand side. Here, let's start with the left-hand side. The left-hand side, we said the gradient of AB. Okay, so what does it mean? Going with the definition, that means we're going to have on I component the partial derivative of AB with respect to x plus on j component the partial derivative of AB with respect to y plus on k component the partial derivative of AB with respect to z. Okay, good. Now look at this. Inside this bracket we have AB, partial derivative of AB with respect to x. Now, going with product rule, that means we are going to have A multiplied by the partial derivative of B plus B multiplied by the partial derivative of A. Hello? Yes, that is product rule. Now, let's go there. We have on I component, we have A multiplied by the partial derivative of B with respect to x plus B, the partial derivative of A with respect to x. Now, let's go to j component. We repeat the same thing. A multiplied by the partial derivative of B with respect to y plus B multiplied by the partial derivative of A with respect to y. Okay, and then also to the k component, we have A multiplied by the partial derivative of B with respect to z plus B, the partial derivative of A with respect to z. All right, yes. Now let's use this component ijk to open the bracket. So that means we are going to have A, the partial derivative of B with respect to x, I, plus B multiplied by the partial derivative of A with respect to x, I, plus A multiplied by the partial derivative of B with respect to y, j, plus B multiplied by the partial derivative of A with respect to y, j, plus A multiplied by the partial derivative of B with respect to z, k, plus B multiplied by the partial derivative of A with respect to z, k. All right, good. Now, as we just open everything, let's collect like terms. The like terms we want to collect is all the partial derivatives that are multiplying A. Let's bring them together. And all the partial derivatives that are multiplying B. Let's bring them together. Okay, now you see that all the partial derivatives that are multiplying A are actually the partial derivative of B. Okay, so that means we bring all the partial derivative of B one side and all the partial derivative of A one side. So doing so, look at what we are going to have. We're going to have A partial derivative of B with respect to X, I component, plus A multiplied by partial derivative of B with respect to Y on J component, plus A partial derivative of B with respect to Z on K component. Okay, these ones are the partial derivative of B and they are all multiplying A. Now, going to the next one, we bring together all the partial derivative of A that are multiplying B. Okay, now we get them together. We have B multiplied by the partial derivative of A with respect to X on I component, plus B multiplied by the partial derivative of A with respect to Y, J, plus B multiplied by the partial derivative of A with respect to Z on K component. All right? Yes. Now, carefully looking at this, we see that in this first one here, we have A multiplying all. We can actually factor out A. So factor out A, look at what we are going to have. We will have A open bracket. On I component, we have the partial derivative of B with respect to X, plus J, the partial derivative of B with respect to Y, plus K, the partial derivative of B with respect to Z. Okay, we put this in bracket and then we say B. You see that B is in all, so we factor out B. So factoring out B, we have B open bracket. On I component, we have the partial derivative of A with respect to X, plus J, the partial derivative of A with respect to Y, plus K, the partial derivative of A with respect to Z. All right, yes. Now carefully looking at this and then going with our definition, we can see that the inside bracket is partial derivative of B with respect to X, Y, Z on I, J, K component, which is exactly what we mean by the gradient of B. Okay, which is the definition of a gradient of B. Now we say that this one is a gradient of B. All right, yes, that was a plus. Looking at the second bracket again, we see that this is the partial derivative of A with respect to X, Y, Z on I, J, K components. All right, so here we say that this is B gradient of A. Hello. Now, that means we just found out that this is A, the gradient of B, plus B, the gradient of A. Okay, so therefore, hence the proof. We have the gradient of AB is equal to A, the gradient of B, plus B, the gradient of A. All right, yes. Thank you very much for watching. If you like the video, please give it a thumb up, subscribe, share our videos, and stay blessed.